So today we're going to first say a few words about the elementary row operations. And these we can denote this ERO. And these elementary row operations, they look like this. The simplest one is RI is exchanged with RJ. The second type of elementary row operations is we have just a constant times RI. So one of the rows is multiplied by a constant number. And the third elementary row operation is the following, where Rj star is equal to Rj minus lambda Ri. Okay, and we know how we have used this before, but today we're going to see how these elementary row operations, they can be determined using a matrix. One thing that we have to be careful is that when we were solving systems of linear equations in the last session, you remember that we were trying to solve this equation, and this equation we constructed first the augmented matrix, right? So this is how we got this before, and from the augmented matrix we try to simplify it. And the definition of the simplification, it's called like the efforts to produce as much zeros as possible. And when we do this, I guess you all remember that we used to use extensively this expression, right? So we used to use this one, which meant that we were trying to affect row 2 and row 3 by using row 1 as a pivot, and so on. But we have said that the matrices, they can be used as linear operators to describe any change in the system. So in this time, we are going to see how...
Professor.
Yes.
Can you shut off the curtain, because it's reflecting with the board?
Shut off. Okay, actually I tried. I want this kind of feedback from you. So if this is the case, let me try this again. I tried. Is it so bad?
Try the other window. I see a couple of other windows.
The curtains. Is it better?
Let me get what they're gonna do.
A little bit.
Okay.
Professor, can you explain again the third formula?
Is it better?
Yes.
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 Okay, that's good. Now, did you have a comment on the class, or did you say something? You said, were you talking only about the curtains or also about the material? Okay.
Looks good now.
She said, explain the third formula again.
Okay, the third formula, thank you for reporting this. So the third formula, what this is, you are trying to change the values in a specific row using the previous row as a reference. Okay, so this is what we have done. And traditionally, we can solve a couple of examples. When we come to the examples, if we still don't understand it, you ask me once again. Okay. So this was an elementary row operation, and you remember that we use the first row to change a little bit the second row, the first row to change the third row. So there are a series of different effects or different changes. But now you know mathematics, and you know, for example, how when you have x. Let me give an example. So you have here x, and you have a function f of x is equal to x squared, right? G of x, sorry, this is g of x, this is equal to x minus 2. And h of x, this would be 1 over x. So let's assume we have these functions. And then if we want to find what is f of g of h, how do we find this? this whole thing, this would be equal, we first calculate h of x, then the result, so let's find what is h of x. H of x is 1 over x, that's good. So this is f of g of 1 over x, and then we get what is g of x, so we apply this one now, okay? This becomes f of, what is g of x? X minus 2, okay? So this becomes
1 over x.
yes, how would this be?
We substitute 1 as the x.
1 over x minus 2.
Yes. Okay. So this is how this would be. And then what is the f of x here? This is 1 over x minus 2 all squared, right? So this is how we do this. And now we can say that what is this? This one, this is a, let's say, capital H of x, which is equal to f of g of h of x. So what we're trying to say here is that always when we apply a linear transformation on a matrix, we put next to the matrix that we are changing the first matrix, then the second, then the third, and like this. So sometimes it might be confusing, but think about this one. This is a completely equivalent to these functions. And the linear matrices, they are like transformation functions, which are going to modify the matrix a little. Now, as we go on, we're going to define elementary matrices, which we call them EM, or let's call them for today in this class as E. Okay? So we have elementary matrices. Which today, let's define them E. They are matrices that are derived using ERO. What does ERO mean? Using elementary row operations on identity matrices, on I n by n. Okay, so this is an elementary row operation. So for this, let's define a matrix which looks like this: 1 minus 1, 2, 2, 0, 7, 1, minus 2, 3. Okay? So here we have a matrix A, and we want to do a change in this matrix such that, so let's say we want, or let's do the following. Wait a second. So let's apply a row operation, which is going to be like this. Row 2 star is equal to row 2 plus 4 row 1. Okay, so this is an elementary row operation, which is like this. So before a while, you asked me what this was about, and the way to do this is the following. So we just say that to do this change, the first row, this is the pivot row. This does not change. 1 minus 1, 2. And the second row, it will be like this. Row 2 plus 4 row 1. What is row 2? Is 2, 0, 7. What is 4 row 1? It is 4 minus 4, 8, right? So we do it like this. So then we are adding these together, and all we get is 6. Okay? Thank you for your feedback. So we get here 6 minus 4, 15. So this is how we apply it. We write it down immediately here. Then we get 1 minus 2, 3. So this is an elementary row operation, ERO. But we did this on a matrix A. Okay? This is a matrix A. Now, we can, but let's see now, what is the elementary matrix that we are talking about? We say that we derive this E from using ERO on identity matrix I and N. So let's assume an identity matrix that looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? Let's try to conduct the same linear operator on this matrix. What are we going to get? Can somebody help me here? So I'm saying, let's use this. elementary row operation in here.
It's going to be 0. Yeah.
And then,
1, 0.
okay, that's good. So this is an elementary row operation. So let's try to do this. Allow me to delete this one because I believe we understood this. And let's apply this matrix on this elementary matrix here on this. So here we have 1, minus 1, 2, 2, 0, 7, 1, minus 2, 3. And here let's multiply with this matrix, which is 1, 0, 0, 4, 1, 0, 0, 0, 1. So let's multiply it with this matrix.
The first row and won't change, I think.
Yes, the first and the third is not going to change. You are correct. So let's write it down. 1
Minus
2, 3. What about the second row?
We can multiply 1 and add 2, which will do 6.
Say it again.
4 multiplied by 1 and add 2. 6.
6.
1 multiplied by 0 minus 1 multiplied by 9, I think.
Do we get 9 in the end? Okay, 4, 8, and 7, 15, right? Because
No.
we have 4 times 2 is 8, plus 1 times 7, it is plus 8 plus 7 is 15.
Yes.
Okay, now we can compare this result here, okay, with this result. It looks like they are the same, right? They are equal. So what we understand from here is that the linear transformation, which is represented by this operation here on this matrix, it is equivalent to multiplying this elementary matrix E on the matrix A, okay? But let's not forget, how did we find this matrix E? We find this matrix E by starting from the identity matrix. So now let's try another operation, which would be the following. Let's do this. What is R2 squared equal to R2 minus 4R1? Okay. So let's have this other, and let's see what we're going to find. As you proposed before a while, you mentioned that the first row and the third row probably is not going to change. So here we have 1, minus 1, 2, and 1, minus 2, 3. And then let's see what we get here. Row 2 minus 4, row 1.
2.
What do we get here?
The same
2.
as the first one. 207.
207. Okay. So we see that from this matrix, we do this linear, we do this change, we obtain this, we apply this other one, we go back to where we were. So we notice that this matrix here, this is the same with this matrix here. So one way, we can say that this transformation is the inverse of this transformation. Why do we call this inverse? Because we know from mathematics that these functions here, f of x, g of x, it could be sometimes that we denote these like f, we have f and f inverse, right? So this can lead to this. And f of f inverse of x is equal to what? What is this?
X.
X, that's true. So this is equal to x. So the same principles or the same logic that we use in the functions, we use it also in the matrices. Matrices that also have an inverse matrix. So if we have a vector x, we multiply with the matrix A and inverse A times a vector x. We still get a vector x. Okay, so the same principles remain. Now, I might strongly suggest to you two things. The first thing is try to think, when you multiply with a matrix, try to think as if you are applying these functions. Because this gives a more pure understanding of how you are dealing with these matrices. Okay, so first thing is, for any matrix, consider it like a linear transformation because that's what it is. And always go back and see the equivalence with what you have done so far with functions like f of g of x, Fogel and Goffey, here. So first thing is, think the matrix operations like these functions, which were shown here. Second thing is that whenever you do any change in a matrix, rather than doing this, try to do this, okay? Implementing linear transformations like these in this form, it will serve you better. There are some courses where this representation, it will be much more intriguing, and also it will educate you better. Okay, so try to keep in mind these two aspects. As engineers of the future, this approach, it will greatly help you. Now let's try to see what we get from this identity matrix. Let's apply this linear transformation on this matrix here, on the identity. So probably the first and the third row, they are not going to change. So the only row that is going to change is the second row. Now let's do row 2 minus 4 row 1. What do we get here?
Minus
Minus
4.
4.
And then we get this, okay? So let this be E1, okay? Elementary matrix E1, and let this be elementary matrix 2. So if we multiply the, let's say, this result with E2, so this is E1. So if we multiply this result with E2, what could we get? So we have here 1 0 0, 1 0 0, minus 4 1 0, 0 0 1, multiplying with this 1 6 1, 1 6 1, minus 1, minus 4, minus 2, 2 15 3. Now let's see what we get. The first row stays the same because this is 1 0 0, this is 1 minus 1 2, and then we get here, since this 0 0 1 is going to multiply these elements, the first two elements here will be multiplied by 0, so we will simply say that we get 1 minus 2 and 3. And then let's see what we get here. When we multiply this row with any one of these three columns, we get minus 4 plus 6, we get 2, and 4, this, and then we get here a 3. Wait a second, so this is,
I think it's 7.
minus 4, 7. Okay, 7. So it looks like we obtained here the following. This matrix here, this is called E2, okay, because this is how we call this one, E2 times what? We multiply this matrix, which we got it from here. What is this in itself? This matrix here, this is E1 times matrix A, okay? This is E1 times matrix A, and this was equal to what? What did we find here? So reminder, this is E2, this is E1 times A, because this is, so let's not forget, this was A, E1 times A, we got this. Let's call this one B. Maybe it's better if we call it B, we don't get confused. So, what was the answer here? This is E2, this is E1 times A. What is this?
A.
It's A, okay? Now, in matrix multiplication, we know that if we have a series of matrices and we multiply them with each other, we can always do the following. We can multiply the first two, then times the third. Or we can multiply the second and the third times 1. So it doesn't matter. So here, we can even say, so from this expression here, we can denote, where should I write this one? Let's do this here. So instead of this, we can write also this E2 times E1 times A, this is equal to A. What do we understand from here? So from here,
E2 is the inverse of E1.
That's correct. E2 is equal to E1 inverse, okay? So they are inverses of each other, because this means that this product is equal to identity matrix times A. This is equal to A. So this is true. But two matrices, when we multiply two matrices, that's equal to identity 1. That's what we get. So it looks like this is a function or a linear transformation. This is also another linear transformation. And then if we apply these two linear transformations, we find these two matrices. And apparently, they are inverses of each other. In order to confirm this one, what you can do is that you get these two matrices, E1 and E2, multiply them, probably you are going to get an identity matrix. Okay, so these are elementary matrices that we define them this way. And another thing that we can add here is also the fact that, for example, I guess let this be A and let this be B. If we can go from matrix A to matrix B using a limited number of elementary row operations, then we call the A and the B row equivalent. Okay, so A and B is row equivalent if we can obtain them using the multiplication with matrices of this type. Okay, what is this matrix? It's called an elementary one because it's simply derived from the identity matrix, as we explained. Now, let's see. Let's try to pick an example. Maybe the best one could be if we went over. Wait a second. First. Okay, so let's do this one. 1, 2, 4. Let's have a matrix which is equal to 1, 2, 4, 1, 3, 6, minus 1, 0, 1. So this is a matrix, and let's assume that we want to obtain the reduced row echelon form. What was the reduced row echelon form? It was a matrix where we wanted to have as leading, and on each row, we wanted to have leading ones. And the objective was to make these zeros. So first, we try to make these zeros, right? And then we try to make some more zeros around here, okay? So we want only the diagonals to survive. Is it possible? Yes, it is. Is this the only way to do it? We could also try to make a non-zero here, non-zero here, and non-zero here, which means that we could keep non-zeros one number per row. But this is the most elegant way, because I had the student asking, why, professor, why are we making only the diagonal non-zero? This is the most optimal way, because this is the only way that we can have all the rest being equal to 0. Okay, so we start with this matrix, and let's see what can we obtain in the end. But one thing that we can try is the following. We remember that when, or actually, this problem we can define it in two different ways. But remember, I guess you remember the following. That when we have AX is equal to B, what did we used to do? We used to have this augmented matrix, okay, which we spelled it like this, augmented matrix. What was augmented matrix? We wrote the A, we merge the B, and we do the changes in A and in the B, okay? So here, for a moment, let's augment here the 1, 0, 0, the identity matrix. Okay, and let's try to obtain reduced row echelon form. So let me erase this one here. Let's say here, get RREF, reduced row echelon form, for this matrix here. Okay, let's do it.
Equals row minus 1.
Sorry, is this my network problem? Your sound is coming like with discontinued. What? Can you repeat it again?
Row 2 equals row 2 minus.
Row 2 star is equal to row 2 minus row 1. Okay. So apparently we use row 1 as a pivot. What about this other 0? How can we make this 0?
Row 3 star plus row 2.
plus row 1. Чего? Какой интерес? А потом у нас зерен шел сейчас under prayer, а лаютьев.
Under prayer.
Папну Петучева. Съешь совсем?
Mender prayer, Johnny.
Under prayer, John.
Oh,
Okay, so let's see what we get here. So we're going to modify, row 1 is not going to change, it's a pivot row. 1, 2, 4, okay, and this is 1, 0, 0. Then the second row is going to be row 2 minus row 1. We just subtract 1,
0, 1,
yes,
2.
okay, what about here?
Minus 1.
1. What about here? Row 1 plus row 3. So we have these two, we just add them together. What do we get here?
0,
Yes.
2, 5.
What about here?
1, 0, 1.
We get this 1. Okay. Okay, then the next step is to produce a 0 in here. So how can we make the 0? We can say that row 3 star is equal to row 3, then
Minus 2 times row 2.
Yes, minus 2 times row 2. Then we move here and we get the following. This is 1, 2, 4, 1, 0, 0. And here the row 2, second row is not going to change because it's a pivot row. This is minus 1, 1, 0. And here we get 0, 0 because this is 2 minus 2, 0. And then we have 1. Okay, what about here? Row 3, this is 3, 0 minus 2
Minus 2.
Okay,
1.
1. Okay, so we did the first task, okay? Now these are all zeros, that's good. What is the next task? Next task is to produce zeros up here.
We can write
Yes?
row 1 star equals row 1 minus 4 row 3.
Is equal to, again, repeat it again?
Row 1 star equals row 1 minus 4 row 3.
Yes, minus 4 row 3. Okay, so let's see. So the third row does not change because it's a pivot row. And here we get 0, 0, 1. This is 3 minus 2, 1. And then the row 1 is row 1 minus 4 row 3. So this is 1 minus, this is 1, 2, 4 minus 4, 0. And then we have 1 minus 12 minus 11, 0 plus 8, it's 8, 0 minus 4, minus 4. What about row 2? What can we do to row 2?
Row 2 star. Yeah.
Oh, okay, so we go with this, and then we get 0, 0. And row 2 minus 2 row 3, this is minus 4, minus 6, minus 7. Then we have 1 plus 4, this is 5, and 0 minus 2 minus 2. Okay. So we are left with only 1, 2. How can we make a 0?
We can write row 1 star, which will equal row 1 minus 2 row 2.
Minus 2 row 2. Okay. And then we come to this point and we get this is 0, 0, 1, 0, 1, 0, and we get 1, 0, 0. So apparently we got the identity matrix here. And then we're just modifying the first row. This is minus 7, 5, minus 2, 3, minus 2, 1. And this is row 1 minus 2, row 2. Row 1 minus 2, row 2. What are
3 minus 2, 0.
3 minus 2, 0. Okay, so what did we do here? So we obtained the following. So we had a matrix A, which we can write it here. And this was 1, 2, 4, 1, 3, 6, and minus 1, 0, 1, minus 1, 0, 1. The first thing we did here, it was row 2 minus row 1. So if we write here, so this is the very first operation that we did. How do we do it? We can do it using an elementary row operation. How does the elementary row operation look like? It's going to look row 2 minus row 1. What is row 2 minus row 1? This is going to be minus 1. This is all, okay? So this is E1. Okay? Then what was the next operation? This was row 3 plus row 1. How can we represent it? 1, 0, 0, 0, 1, 0, 0, 0, 1. So what we're trying to do here, we're trying to do all these operations to represent it as linear transformation that are implemented by multiplying with a matrix. So this is the identity matrix for now. And this is row 3 star is row 3 plus row 1, which means that this will be 1. Why? Because from the identity matrix, if we add the first row and the third, we get this. So this is E2. And then we say row 3 is equal to row 3 minus 2 row 2. Okay. This means that we can get another identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And again, let's have a look. That's it. That is row 3 minus 2 row 2. Row 3 minus 2 row 2, we just get a minus 2 here. This is row 3. So we can continue like this. What is the next one? Row 2 minus 2 row 3. So we go again. Sorry, I wrote here row 3, but this is E3. So I guess you are faster than me in calculating these. 0, 1, 0, 0, 0, 1. And again, where quickly we done? We are here. Row 2 minus 2 row 3. Row 2 minus 2 row 3. How should I change this? So how should we change this matrix to implement this?
0, 1, minus 2.
1 minus 2.
Yes, thanks. Okay, 0, 1, minus 2. So this is E4. Then let's do this one. How would the identity matrix look like? This is row 1 minus 4 row 3. This is 1, 0, minus 4, 0, 1, 0, 0, 0, 1. This is E5. Okay. Now we are left with the last one, which is this transformation here. Row 1 minus 2 row 2. So this is going to be equal to 0, 1, 0, 0, 0, 1. What should be the first row?
1 minus 2.
Yes, 0. So this is E6. So it looks like, what is this? This is the matrix A. Okay, so it looks like, so all of this work that we did over there, we can represent it like this, E. What do we do to E? First, we apply this function f, right? So what do we do? The first function which is applied, it stays closer to the matrix. This is f, g, h, l, m, k, like the function go feature that we write in this way. So then, what do we get in the end? In the end, what should I write here? What did we get? I think we got this, right? What is this?
Identity
That's
matrix.
correct. We get the identity matrix. So in this, we got the following. Okay. So apparently, what is this then? E6 times E5. E6 times E5 times E4 times E3 times E2 times E1. What is this? Let's call it matrix E. So we have 6 linear transformation, E1, E2, E3. Let's call it E, Shkonya A. What is this equal to? Actually,
The inverse of the matrix A?
exactly, that's true. So if we multiply all of these with matrix A, this is equivalent to, we can do the following. We can multiply all of these matrices and we get this E times A, but this was equal to the identity matrix. So it looks like this whole 6 matrices, this gives the E, but then we imply that E is equal to A inverse, okay? So if E is equal to A inverse, that means that all of these operations that we did here, this means that this is also A inverse. Why? Because we had A, so how did we start here? We started with AI, right? A and identity matrix. And then we did a lot of these operations, and it looks like we ended up finding what is A inverse. So all of these matrices that we applied, so what did we do here? We first applied E1, then E2, E3. All of this was equivalent to applying a matrix which we denoted as E. Okay, we did this, but you also argued, you reported that this is the A inverse. So we applied A inverse, doing all these steps here, which, so this upper part, this is the same thing as we have done it at the lower part here. So there are two different approaches, but we get the same result. So here we have AI times A inverse. What we did is that we multiply the AI, we put this inside this parenthesis. We get A inverse times I. And this is equal to, this is A inverse. And what is this other term here? What is A inverse times I?
A inverse.
Yes. So it looks like we found the A inverse is right here. Okay. So we were lucky to find it, and this is how we ended up into determining the inverse of a matrix using elementary row operations, or doing the job that we followed when we found the solution of a system of linear equations. Okay, so this is the first part we can talk about. We talked about the inverse operators. Then we can also this is elementary row operations. We talked about the row equivalent. So if from matrix A we go to matrix B using elementary rows, we call those row equivalent. I think we talked about that one. Then it is time to mention a theorem. So the theorem states for any matrix A, which is a square matrix. Why is it a square matrix? Because we denote this one as A n n. Then for any square matrix, the following are equivalent. Which one are equivalent? The first statement is that the A inverse exists. The second statement, the AX equal to B has unique solution. So whatever the value of B is, this equation is going to have a unique solution, which means that X is going to define a single point, okay? So it's not going to be a straight line, it's not going to be a plane or something more complex, but it's going to be a unique solution, which means only one solution. And we know that systems of linear equations, they have no solution, 0, 1, or infinity. Okay?
Infinity.
That's correct. So we never have a system of linear equations having two solutions. That doesn't happen. But it looks like this one can have one solution, which was one out of the three options. And this is probably the best option because we have a unique solution, which makes also that if this is the case, then inverse of a matrix, it exists. And then third, what is equivalent to this is that for AX is equal to 0, this system, it has only the trivial solution. What do we understand with trivial solution? With trivial solution, this means the following. It has only this solution when x is equal to 0. Okay, this is a trivial solution. It is the same way as saying the following. 3x is equal to 0. What is x? It's 0, right? So if 3x is equal to 0, what is the solution? This has only the trivial solution. Now this is the third statement, and the fourth statement is reduce the row echelon form of A. This is equal to the identity matrix. So this is the
Inverse A exists if its determinant is different than 0.
I think that's correct, yes. And I believe we have seen this one. Why would you say so?
AD minus BC should be different than 0 because it is a numerator.
Yes, that's right. So in a 2 by 2 matrix, so let's start with determinant then. So you are saying that inverse of a matrix, it exists if the now, okay, in the next 5 or in the next 10 minutes, I'll try to go over an interesting example, but probably we could, do you have any question for what we did so far? Is everything clear?
Yes.
Okay, thanks.